Angular momentum. Angular momentum of a particle with respect to a well-defined origin is defined as L equals R cross P. Note this is not a multiplication, but this is actually a cross product, where L is the angular momentum of the particle, R is the position vector of the particle relative to the origin, P is the linear momentum of a particle, and R is the vector cross product. The derived SI units for angular momentum are newtons, meters, seconds. Because of the cross product, L is a pseudo-vector perpendicular to both the radial vector R and the momentum vector P, and it is assigned a sign by the right-hand rule. So since angular momentum is a vector, its magnitude is given by RP sine theta or PR sine theta. Okay? When the angle between R and P is 0 or 180 degrees, there is no perpendicular component, and the line of action of P passes through the origin, and R perpendicular is 0, which implies that the angular momentum L will also be 0. Now let's do this proof. We want to show that the sum of the torques is equals to dL over dt. Or, in other words, the net torque acting on a particle is equal to the time rate of change of its angular momentum. So I want to prove sigma torque equals dL over dt. This is what we need to prove. Okay? So let's start with the definition of L. What is L? Angular momentum is R cross P. Correct? Okay. Now, in order for me to find dL over dt, I am going to differentiate both sides by d over dt. Okay? So that means I'm going to have, if I do this, dr over dt cross p plus r cross dp over dt. Okay? What is momentum? Momentum is this can also be written as velocity times mv plus R cross dp over dt. Okay? Now, what is this vector? This can also be written as mv cross v. Right? Velocity cross velocity. So the sign of the angle between a cross product will be a v dot v sine of theta. If these both are v's, the angle between them is going to be 0 degrees. Sine of 0 is 0. So this whole thing goes to 0. Okay? Plus r cross d over dt of mv. Right? This means I'm going to have a plus r cross m dv over dt. Okay? What is dv over dt? So this becomes 0, right? What is dv over dt? This is equals to r cross ma. It's acceleration vector. And ma is equals to force. So r times f is also equals to the sum of the torques. So this side, it becomes the sum of the torques. And this side, we were going to get dl over dt. So hence, we have proved that dl, the rate of change of angular momentum, is equals to the sum of the torques. So now let's do a problem. A particle of mass m is released from rest at point P, falling parallel to the vertical axis. Find the torque acting on m at any time t with respect to the origin. Find the angular momentum of n at any time with t with respect to the same origin. And C, show that the relationship delta torque dl over dt yields the correct result when applied to this familiar problem. So let's walk through this problem. In this problem, it says a particle is released from rest at a point P, which is given here, right? It's released from rest, so its initial velocity is equals to 0 meters per second, right? And it says that it is falling vertically parallel to the vertical axis, so it's falling, I believe, like this, right? And then it says find the torque on M at any time t with respect to the origin. Okay, so we know for part A, my torque is going to be R times F. Okay, that means it's going to be RF sine theta, right? Where theta is the angle by which it falls. And I know this is going to be, if I rewrite this, oops, that looks like cross, but this really isn't. So this is going to be R sine theta. And what is the only force that's acting on it? Its weight, which is acting downwards. Okay, now how do I solve this? Well, it's easy to see if this is where the torque is, and this is where the object is, and if we call this one as angle theta, then sine of theta, which is going to be this angle over here, is going to be B, if I call this B. Okay, so this is going to be B mg, and I plug in the values, or in this case they don't give me values, so this is going to be my answer. Okay? Excellent. Part B. In part B it says find the angular momentum of, the angular momentum of M at any time t with respect to the same origin. So in this case I have to find the angular momentum. What is the angular momentum? Angular momentum equals R cross P. Okay? What is R cross P? RP sine of theta. Right? This means it's going to be R sine theta times mv. What is this again? B mv. So the angular momentum L is going to be B mv. Okay? The third problem, it says show that this relationship, for part C, it's saying show that delta torque is equals to dL over dt. So I have a torque and I have an L. Okay, so what can I do? I can actually put in this value over here, which is going to be my torque value, which is Bmg. Okay, for this one, what is it going to be? So I have this L, and L is Bmv, right? So dL over dt is going to be Bmd v over dt, okay? Because v is a function of time. As it falls, it speeds up, right? We know that. Now, what is this v? V, in this case, I don't know, but I do know v equals the rate of change of displacement, or we could also be written as dv over dt equals acceleration. So for our case, this acceleration is going to be only g. So dv could also be written as g dt. And if I was to integrate it, what would I get? Integrate both sides, or just take this dv over dt and plug it into here, which equals bmg. Okay, so the left-hand side of this expression is that, and the right-hand side of this expression is that. Both these are equal, so hence we have proved. Now, what happens if for a system of particles? If a system consists of several particles, the total angular momentum about an origin can be obtained by simply adding or integrating all angular momenta of the constituent particles. Angular momentum can also be calculated by simply multiplying the square of the displacements r, the mass of the particle, and the angular velocity. So for a system consisting of n particles, L will be given as a sum of all the momentas for each particle, and the vector sum taken over all particles will be given by dl over dt, which is the sum of all dl's over dt's. Okay, so for a system of particles, the same thing happens true. The net external torque acting on a system of particles is equals to the time rate of change of angular momentum of the system. Note, the total angular momentum must be calculated with respect to the same origin in an inertial frame. And in situations where there is no confusion that is likely to occur, we drop the subscript on the torque for convenience. So now that we've talked about particle, we went from a single particle to a system of particles, and now let's talk about rigid objects. So angular momentum of a rigid object is defined as the product of the moment of inertia of that object times the angular velocity. Okay, so the angular momentum is the same as the linear momentum in this case for a rigid object. And if there is no external torque on the object, the angular momentum is subject to the conservation of angular momentum principle. Okay? And so here we can obviously see that the angular momentum L is the same as P. I is in place of M and omega is in place of V. They're exactly the same things. Well, not exactly, but they're analogous to each other. So next example is, which has a greater magnitude, the angular momentum of the Earth relative to its center associated with its rotation on its axis, or the angular momentum of the Earth relative to the center of its orbit associated with the orbital motion of the Earth around the Sun? So let's do this problem. So for part A, it's asking me the angular momentum of Earth about its axis. Okay, so here's my Earth, here's its axis, it's going around its axis, right? And it's rotating. So what do I know? I know that the angular momentum rotational is given by I omega. The Earth, I can almost consider it as a sphere. 2/5 r squared, right? In this case, it'll be the mass of the Earth and the radius of the Earth. And what about omega? Well, omega is going to be its angular velocity as it is going around, or angular speed, which is going to be given by 2 pi over t, right? Where t is the period, okay? So mass of the Earth we know, radius of the Earth we know. What is the period of the Earth? Absolutely, it is 24 hours. So then we can convert it to seconds, right? And plug the numbers in. So the mass of the Earth is about, so I'm just going to rewrite it here. Mass of the Earth is about 6 times 10 to the 24 kilograms. Radius of the Earth is about 6.4 times 10 to the 6 meters. And the period is going to be 8.64 times 10 to the 4 seconds. Please make sure that I got those numbers correct. Once you have those numbers, you can just simply plug them in. So we will have L rotational of the Earth about its center is going to be about 7.06 times 10 to the 33 kilograms meters squared per second. Okay, here's one of my, oops, I'm just going to get rid of that. Here's one of my answers, right? Okay, now for part B, it's asking me the angular momentum of Earth in its revolution around the Sun, right? So in this case, we are going to have a Sun in the middle, and then we're going to have the Earth, and the Earth is going around the Sun, okay? So in this case, your angular momentum is going to be given by r cross p, where r is the radius of the orbit, O-R-B-I-T, times p, okay? Which means it is the momentum of the Earth, right? So we can get rid of this because we know what the angle is going to be, 90 degrees between the both of them. So this is going to be radius of the Earth's orbit times mv, mass times mass of the Earth times velocity of the Earth. Well, if I don't know the velocity of the Earth, I do know its angular velocity, right? This is going to be r of the orbit, mass of the Earth, 2 pi over t. Now, which t are we going to talk about in this case? Well, this was t for the day. How long does it take the Earth to go around the Sun? So t, in this case, will be t of the year, which is 365 days. And that we can convert to seconds, right? Once we have that done, we can plug it in here. We can plug in the radius of the Earth, the radius of the orbit of the Earth, mass pi over t. Yes, we realized that the radius of the orbit was going to change because it's elliptical. And understanding that we know that, but we can take an average of all of these numbers and plug them in. When I plug them in, I get it to be 2.6 times 10 to the 40 kilograms meter squared per second. Okay? So compare this to this, and you get your answer. Which one is going to be greater?